In this video, we will find and classify all the critical points of a function of two variables as either local minimum, local maximum, or saddle points. So first, let's just find the critical points, and we'll worry about classifying them later. So remember what a critical point is. It is a point where the gradient vector of the function is either 0 or doesn't exist, or is undefined. So the first thing we need to do is just find the gradient vector. So let's compute that. So the partial derivative with respect to x is 6x squared plus 6y. So let's factor out the 6. And the y derivative is 6y plus, 6x plus 6y. And again, let's factor out the 6. So, one more time, we are looking for critical points which are xy pairs, so that both of these partial derivatives, here is fx, here is fy, we want them both to be 0 simultaneously for the same values of x and y. So let's do this one piece at a time. First, let's look at what it means for fy to be 0. If the y derivative is 0, this means that y is equal to negative x. Now what if the x derivative is 0? This means that y is equal to negative x squared. And we want both of these things to be true at the same time, for the same values of x and y. So if we combine these two, and assume that both are true together, this means that x is equal to x squared. Or if we move things to the other side, that 0 is equal to x squared minus x, which we can factor as x times x minus 1. And now we can easily see that there are two solutions. Either x equals 0 or x equals 1. So there are two critical points. One where x is 0, and then using either of the two equations above, you see that y would also have to be 0. And one critical point where x equals 1, and in this case y would have to be negative 1, since y is equal to negative x, or negative x squared. So we've done half the job now. We have found the critical points. There are two of them, 0, 0, and 1, minus 1. Now we still have to classify them, meaning we have to tell what sort of critical point are they. Are they local minimums, local maximums, saddle points? Possibly neither. So we have to remember the second derivative test. And in the second derivative test, we need this quantity called the Hessian determinant. So before we get into that, we need the second derivatives. So we need fxx, fyy, and fxy, which, if you'll remember, is always the same as fyx. the order in which you do derivatives doesn't matter. So let's look back up above. fx was 6 times x squared plus y. If we take the x derivative again, we get 12x. fyy, the y derivative was 6 times x plus y. If we take the y derivative again, we just get the constant 6. And similarly, if we do fyx or fxy, we just get 6. Now remember this thing called the Hessian determinant. It's the determinant of this 2 by 2 matrix where you put the second partial derivatives. And so it looks something like this. fxx times fyy minus fxy squared. Since fxy and fyx are the same. So in this case, using what we just computed off to the left, this is 12x times 6, so 72x, minus 6 squared, which is 36. And we can factor out a 36. So this is 36 times 2x minus 1. Now the second derivative test is all about this quantity d, this determinant. We need to plug our critical points into this function, d, and depending on what we get, this will tell us what sort of critical point it is. So we need to compute d of 0, 0, and d of 1 minus 1. So first, d of 0, 0, we get negative 36, which is of course negative. And if you remember, when d is negative, that tells you the critical point is a saddle point. If we plug in 1 minus 1, we get positive 36, which is positive. When it's positive, we're not done. When d is positive, this means that it might be a local minimum, it might be a local maximum, but we still have some checking to do. So when this happens, we additionally need to check the value of fxx, or fxy, or sorry, fyy. In this case, fxx was 12x, so this is 12, which is positive. And when this ends up being positive, that means the point is a local minimum. Just to review, if this had ended up being negative right here, it would have been a local maximum.